Okay, the first step is the domain, but in this case super easy because the domain is given in this specific interval. So domain is exactly the same the given interval. Okay, now y-intercept. 2 times 0 is 0, times 0 is 0, is 0, 0. X-intercept. This is a little bit more complicated in this case. 2x minus tangent x. Solving this equation. Es obvio que one solution is 0, but we have two more solutions. Okay, it's not easy to find because it's non-linear equation. So the only possibility for solving this is graphically. Let's do it after in Desmos, but I anticipate that the answer is plus and minus approximately 1.17. So we have two. We have two, no, we have three. 0, 0, 1.17, and negative 1.17, okay? Well, Bernoulli acetone we have, yes. Because I know que tangent pi over 2 is undefined. Entonces we have, suppose que you try to approach the limit, when the x approaches to pi over 2 to the left, well, to pi over 2, no, to the left, no, to pi over 2, just pi over 2, because remember, the interval is only from pi over 2, not necessary to specify right and left of the expression, que is 2x minus tangent of x is equal infinity. Because I know que the graph of the tangent, no these ones, you know, the basic tangent graph look like that. This is pi over 2, this is negative pi over 2. This approaches to infinity, the y value positive, and this approaches to infinity negative. That is the reason that positive infinity. And the limit when the x approaches to negative pi over 2. This part is not important, it's totally irrelevant. The important part in this interval is tangent, and this part is negative infinity. Okay? Now, let's go to the calculus part. Okay, let's compute the first derivative. Derivative 2x is 2. And derivative tangent is secant square equal 0. And you solve this equation. This equation is secant square x equal to 2. Secant x applies square root both sides is plus or minus radical 2. And well, this is secant is the reciprocal of cosine, flip it. And the flip it this is plus or minus radical 2 over 2, no? Rationalization after that. It's obvious that the solution of this is plus or minus pi over 4. This is specifically inside this interval. Okay, let's verify this critical point using the first derivative test. This is negative pi over 4. This is positive pi over 4. This is 0. Remember, this is pi negative pi over 2. It's our interval, positive pi over 2. This is the critical point. So I select, for example, here negative pi over 3. I select here positive pi over 3. Yeah, I select here no 0. 0 no, why not? Because 0 is have no sign. It's 2 times 0 times 0 is 0. So I select, for example, I don't know, pi over 8, and you evaluate that value in the first derivative. Negative pi over 3, pi over 8, and pi over 3. To save time, I want to put directly the answer or the sign of the answer, because I want to save time. So you evaluate this answer is negative. Here is negative value, here is positive, and here is negative. Therefore, this is decreasing, this is increasing, and this is decreasing. So because this is local minimum, and it's a local maximum. And this local minimum and local maximum, if you want to find the value, you evaluate p, the original p, in pi over 4, e in negative pi over 4. And the answer is approximately, well, is the exact answer pi over 2 minus 1, which is approximately 0.57, pi over minus pi over 2 plus 1, which is approximately negative 0.57. So we have two, one local minimum and one local maximum. Okay, now the second derivative. Derivative 2 is 0, and derivative secant square is minus 2 secant square, no secant, no square. Derivative secant is secant tangent. And this is minus 2 secant square x, because secant times secant square tangent x. Entonces, using trigonometry identity, I know que secant square is equal to tangent square plus 1. Entonces we have 2 tangent square x plus 1 tangent x equals 0 in order to find critical value. This is never 0. The only possibility is 0 is tangent. Tangent x is equal to 0. Now tangent is equal to 0 in this interval at x equals 0. And this is the potential inflection point. Let me check. Second derivative test, 0 inflection point, potential inflection point, critical point. And you evaluate the second derivative in pi over 3 and negative pi over 3, for example. You evaluate p second derivative in pi over 3, and you evaluate p second derivative in negative pi over 3. Okay, the answer of this is in pi over 3 positive is negative a radical 3. It's negative, so negative is down. And in pi over 3 is a radical 3, it's positive, it's up. So this is inflection point. The inflection point, by the way, is 0,0. 0,0 is x intercept, y intercept, and also inflection point. Okay, and let's see now the decimal simulation. Okay, this is our curve. We can see clear. We have, for example, 3 x intercept, que es 0,0, negative 1.17 approximately, and positive 1.17. Two periodic asymptotes in pi over 2, negative pi over 2 and positive pi over 2. Now the function is increasing. This is the first derivative. When it's increasing, okay, that part is increasing. And decreasing in the complementary part. Okay. Then we have here a local minimum and local maximum. Okay, likewise, inflection point. We have when the second derivative is negative, concave down, and when the second derivative is positive, concave up. Now 0 is inflection point. Super, fantastic.